Hello everyone, welcome to our discussion of section 12.3, which will be about the geometric sequences and their partial sums. So as you remember last time in section 12.2 we talked about arithmetic sequences and their partial sums, and this is another type of sequence and partial sum that it has a particular pattern associated with it. You remember with arithmetic sequences and series, we had the numbers on the list in the sequence had a particular pattern associated with them. So this is another type of sequence. In fact, I should add here geometric sequences and their partial sums. Okay, so that's also another topic that we will look at. So let's briefly describe what a geometric sequence is. Of the form, so once again the first term in the sequence is called A, and I try to be consistent with what the author of your textbook does in terms of using notation. He's using a lowercase a, and that's what I'm using. AR and AR squared, AR cubed, AR to the fourth, and this is an infinite sequence. It can be an infinite sequence or it can be a finite sequence. So such that A is the first term, in the sequence, and R is something we call the common ratio. So common ratio. Remember with arithmetic sequences we talked about common difference. Remember what that was? For that type of sequence, this is common ratio. So, and we will have more to say about this in the coming examples. And so common which may be calculated by dividing any term in the sequence. And term, I mean each of these. So A is a term, AR is a term, AR squared is a term. Each one of these is a term. Any term, dividing any term in the sequence by the term before it. So to obtain the common ratio for this, we can divide AR divided by A, or AR squared by AR cubed by AR squared. So any consecutive terms, this term divided by that term, by the term previous to it, is going to give us the common ratio. And the common ratio is constant throughout a single geometric sequence. It's going to be different for different geometric sequences, but within the same geometric sequence, it'll never change. It'll always be the same value. And that's how we can calculate it. You can take any of these terms, say AR to the fourth power, and divide it by the term previous to it, and you're going to get the value of the common ratio. And of course, AN would be the nth term of the sequence. That's coming up actually. So you're familiar with AN from previous section 12.2. right? So this is the nth term in the sequence. It's basically referring to the formula we can use to find various terms within any geometric sequence. So, and here's the formula. So an, that is equal to a, the first term in the geometric sequence, times r, which is the common ratio, to n minus 1 power. So this is the general formula for any geometric sequence. So if you, in any geometric sequence, if you know the first term, the common ratio, then you can write this formula for any term within that geometric sequence. And then somebody comes up and says, what's the 30th term in the geometric sequence? You can simply plug in for n with 30, and you can calculate what that value is, which appears in the 30th position within that sequence. Okay, talking about that, let's also introduce the formulas for the partial sum of this of any geometric sequence before we look at some examples. As a matter of fact, it's better if I go to a new page because I won't be able to fit all that in the rest of this page. Okay, so that's that. So the formula for the partial sums of geometric sequences is as follows, but I'm thinking I should break this up into cases. I think that's better. So let me do that. Let's see. Yes, so let me do that. So we're going to say case 1. I don't think this is how your book talks about it, but I think you can better remember these different cases under the partial sums if they're broken up into cases. We didn't have different cases for the arithmetic sequence, but in this case we do. So that's why it's important that I highlight that, I think. So let's say case 1. Okay, case 1. So to determine the partial sum of a finite geometric, that's the key word there, finite geometric sequence, we have this formula. We have S sub n, that's partial sum, is equal to A times 1 minus r to n power divided by 1 over minus r. Okay. So we already know what every variable is here. R is the common ratio. N is how many terms we are adding. So let me make that clear in case it isn't. So N here means a different thing than here, than in this formula, which, by the way, I should also clarify here that N, let me put that right on top of it. N here is the location of the term we are finding. So in this formula, N if you're looking for the fifth term in the sequence, n is 5. If you're looking for the 11th term in the sequence, the n would be 11. 20th term, n would be 20. Okay? That's what n and a represent here. But here, n, and I started out with n, so let me describe it here. N is the number of terms we are adding or summing. The number of terms that are being added. Like I said in my last video, this is the thing I worry most about, because your book keeps these variables the same, a and n, and a and n in different formulas, but they mean different things. So please be extra careful and pay particular attention to what these variables mean within the different formulas for the sequence and for the partial sum. And then the a is the first digit, not in the sequence, but in the series, in the number of terms we're adding. So the first digit of the chunk of numbers we are adding within the sequence that are being added within the sequence. Okay? So if you're adding, let's say, the fifth term through the 16th term, right? If you're not starting the add from the first digit in the sequence, but you're starting the addition from the fifth or the sixth term right through all the way to the 16th digit, then the first digit in here, in the partial sum, is the fifth or the sixth digit. So wherever you start adding numbers, that number, that first number where you start, becomes a in this formula. Okay? And n is that, how many terms you're adding, and of course r is the common ratio. So r stays the same. Fortunately, that's one of the variables whose definition is the same in different form in both formulas. So r is the common ratio. Okay? So that's case one. If we're calculating the partial sum of a finite geometric sequence, or you can say, or if, I'm just going to add to that, or if we are adding a finite number of terms from an infinite geometric sequence. That means you can still use this formula if you have an infinite geometric sequence, but you're taking a finite chunk of that for your partial sum. So you have this infinite geometric sequence, but you want to add, say, from the 100th term in that sequence all the way to 150th term in that sequence. Then you can still use this formula. As long as what you're adding within a geometric sequence is finite, you can use this formula. Then the second case is if you have an infinite geometric sequence. So let's call that case 2. Okay, case 2. So to determine the sum of an infinite geometric series, infinite geometric series, this is the critical part, if absolute value of r is less than 1. Okay, so anything positive but less than 1, something between 0 and 1. Okay, so if you have that, to determine the sum of the infinite geometric series, if this, then this is, all of this is important, so I'm going to switch colors. The sum converges to this sum. So S equals A divided by 1 minus R. Okay? So if you have an infinite geometric sequence or series such that the common absolute value of the common ratio is less than 1, that means any number between 0 and 1. Okay? Then the sum, the sum of all terms, this calculates the sum of all terms in an infinite geometric sequence. You can use this formula. So what's happening is that, this is actually this formula. But when n becomes infinite, when this r, when absolute value of the common ratio is less than 1, and this n becomes infinite, then this term reduces to 0. I mean, it approaches 0. When I say approaches, this is a concept you'll become familiar with in Calculus 1. But this being a pre-calculus course, it's kind of implying that way or that idea which is coming up in Calculus 1. But as r is less than 1, something between 0 and 1, any number between 0 and 1, and n becomes infinitely large, I don't know, 100 billion, 100 trillion, something very, very large or infinite, then this term reduces to 0. So 1 minus 0 is just 1 divided by 1 minus r times a, which gives us this formula. So this formula is connected to the formula you saw for case 1, but it's been adjusted for an infinite case where that second term drops to 0. Okay? So case 3, the sum, again, this has to do with the infinite geometric sequence or series, is the sum of an infinite geometric sequence, so this should be sequence. Geometric sequence when, if, I should say, so if, remember for case 2 we had if absolute value of r was less than 1, right? So if absolute value of R is greater than 1, the sum of an infinite geometric sequence, if that's the case, does not exist. So there's no need for a formula for that. Okay? If you have in an infinite geometric sequence, this is not for a finite one. For a finite geometric sequence, you always have a sum. You always have some value for the sum, as long as it's finite. But if you have an infinite geometric sequence and the common ratio is greater than 1, you can never have a sum. It does not exist because the series keeps getting bigger and bigger, bigger and bigger. Because the absolute value of R is greater than 1. So this value keeps getting bigger and bigger and bigger, and it just doesn't matter how big of a number you end up with. There's always a bigger number than that. So therefore, because it's diverging. Let me add that as a matter of fact. The psi1 of an infinite geometric sequence, if it diverges. So here we said the sum converges for case 2. The sum, the sum of that diverges. That's how I should state that. Diverges. Therefore, because it diverges, therefore the sum does not exist. Okay? If absolute value of R is less than 1, the sum converges to this value that you can calculate with this formula. But if absolute value of R is greater than 1, then the sum diverges and it does not exist. Okay? Okay, so let's look at some examples. Okay, so given the nth term of a geometric sequence, and I should write that down, we are given this, an is 3 times minus 4 to n minus 1. So we have the formula for the nth term of this geometric sequence, and it says find the first 5 terms of the sequence and state the value of the common ratio. So let's do that. So here's the solution. A1 is 3 times minus 4. N would be 1, right? 1 minus 1. And this is equal to 3 times minus 4 to 0 power. And then anything to 0 power is 1. Right? 3 times 1, so we get 3. The second term, they want us to find the first 5 terms, so the second term is A2, 3 times negative 4. For n, we plug in with 2, minus 1. And then 3 times minus 1, 2 minus 1 is 1. So we have 3 times minus 4, which is minus 12. Right? A3, or the third term in the sequence, is equal to 3 times minus 4. Instead of n, we plug in with 3, minus 1. Then we have 3 times minus 4. 3 minus 1 is 2. 3 times minus 4 squared is 16. And we have 48. Okay. The fourth term, which is A4, is equal to 3 times minus 4 raised to, let's replace n with 4, minus 1. So we have 3 times minus 4. 4 minus 1 is 3. And this 3, because it's odd, it preserves this negative sign. So 3 times minus 64. And then 3 times minus 64 is minus 192. Please do verify these numbers with your own calculations. And the fifth term, or A5, let's find that by plugging in for n with 5. So 5 minus 1 is 4. Then this 4 is even, which means it cancels this negative symbol. It will end up with a positive number then. And 4 to 4th power, let's see what that value is. So I don't have that in my notes. We're going to calculate it. So 4 to 4th power, because negative doesn't count, right? Because 4 is even. So I'm just going to raise 4 to 4th power, and we end up with 256. So 3 times 256, and that gives us 768. Okay? And then also they ask us for the common ratio. Common ratio, you can take the ratio of any of these. Take the easiest one. Any consecutive numbers, right? You don't want to divide 48 by 3. You want to divide 48 by negative 12. You don't want to divide 768 by negative 12. You want to find the common ratio. You divide 768 by minus 192. So I'm going to pick the easiest one because it's always the same for any consecutive numbers. So I'm going to divide negative 3 by 4. So the common ratio which is equal to R is equal to negative 12 over 3, easiest values, and negative 4. And this is our common ratio, like that. Let's do another example. Suppose we want to find the nth term with given the nth term of a geometric sequence with given first term A. I will list these. So I just want to state the problem the way it was stated in your book. And common ratio R. And So they want us to give the formula, find the nth term. We need to find that. So that is a question mark right there. And also, at the end of this, they say, what is the fourth term? Okay. And this is the information they give us. A is equal to square root of 3, and R is equal to square root of 3. Okay? So, we know that the nth term is this formula, right? We have that, a times r to n minus 1 power. This is for all. So let's plug in for the values for a and r that we have. So this we're finding a specific case there. So an is equal to square root of 3 times square root of 3 again to n minus 1 power. We can simplify this, right? Let's simplify it. Because this term, this second term, we can rewrite as an equals square root of 3 times 1 over square root of 3. That's the negative 1 part. Okay, that's the negative 1 part times square root of 3 to n power. So you can, let me extend this so you can, I hope I didn't confuse anybody by doing that. So square root of 3, that's the first one. You can split this. You can split this term into two terms by saying square root of 3 to n power. Well, let me do it this way. To minus 1 power times square root of 3 to n power. Okay? You can split that because when the bases are the same, we learned this in Math 124 and Math 126. This is a property of powers. When the bases are the same, you can add the powers. So I split it. So now you have that and that. Then this middle one is that. It's just 1 over square root of 3. So, and then square root of 3 to the n power is that. So now this and this will cancel. We end up with an is equal to square root of 3 to n power. So that is the final nth term formula for that, for this problem. Okay. Then they want us to find the fourth term. So all we have to do is plug in for n with 4, right? So let's do that. So this will be the fourth term is as follows. We have a to the a4 is equal to square root of 3 to 4th power. So what do we get? Let's find out. So I'm going to open the parentheses, then take the square root of, square root of, nope, that's not what I wanted. So like that, square root of 3 close parentheses, and raise that to 4th power. You got to be very careful when you use these calculators to make sure that everything, the order of operation is going to apply properly to your input in the calculator. So like that, it's 9. Okay? And then so that's the 4th term in this geometric sequence. Okay. Let's do another example. Determine whether the sequence is geometric in this question, and if it is geometric, find the common ratio. Okay. So here is the sequence we have, and 3, -1. It's an infinite sequence. So if this is a geometric sequence, then if you divide -9 by 27, or 3 by -9, or -1 by 3, you should get exactly the same number, which would be the common ratio. So let's do that, because not only that step not only verifies that this is a geometric sequence, it'll tell us what the common ratio is. Or if it's not a geometric sequence, that'll come out too. So let's do that. So to have a geometric sequence, a common ratio must exist. It's as simple as that. Okay, so let's show whether or not it does. Okay, so -9 divided by 27, right? This divided by the number previous to it, we can simplify that to -1/3. Okay, so far this doesn't give us any information unless we find the next couple of ratios that are equal to it, then we know that we have a geometric sequence. So far we know nothing. So let's divide 3 by -9. What do we get? Again, we get -1/3. Okay, so far so good. Looks like we do have a geometric sequence. And then also, let's divide -1 by, that's obvious, right? -1 divided by 3, -1/3. So because all of these, a common ratio exists, therefore this is a geometric sequence. So we partially answered the question, and of course let's complete that answer by saying that R is equal to -1/3. Right? So that's that. Okay, so let's do a similar example again. So let's make that part B. So let's make this part A. So I'm going to add, so this is part A, and then because we're doing the same thing, I didn't want to write it down, the same problem statement. So this is part B. All right. So this time the sequence is as follows: e squared. We know about e, right? When we talked about natural log, we became in Math 126, Pre-Calculus 1, we talked about that a lot. Okay, e squared, e to the 4th, e to the 6th, e to the 8th, and of course this is an infinite sequence. So there you see that. Okay, so once again we have to show the same thing, whether the common ratio exists or not. Let's do that. E to the 4th divided by e squared. This will simplify, right? This will simplify to that, which is e squared. So far, we know nothing. We have to show that the same ratio exists when we divide the other numbers. So let's do that. So e to the 6 divided by e to the 4. This will be 6 minus 4. E squared, okay, again, the same ratio, right? And finally, e to the 8 divided by e to the number before it, e to the 6. So this will be e to the 8 minus 6 is equal to e squared. So indeed, once again, we have a geometric sequence. So this is a geometric sequence. And R is e squared. You know, it just occurred to me that maybe I should add something to this question. So let me modify this and add this to it, and I'll use my, well, let me use my thicker marker here and say, does the partial sum exist? Partial sum exists. I mean, in each case, right? Does it exist here? What do you think? Does the partial sum exist in this problem? It should, right? So the partial sum exists because the absolute value of R is less than 1. So we're going to add here that the partial, well, let me explain it this way. So absolute value of R is equal to absolute value of minus 1/3, which is equal to 1/3, and this is less than 1, right? It's less than 1, therefore the partial sum exists. Exists because the absolute value of the common ratio is less than 1. So we know we can calculate the sum, the partial sum. It exists. What about here? What do you think? So the common ratio is e squared. What is the absolute value of that? Is it less than 1 or greater than 1? It is greater than 1. So the sum does not exist. So let's make that statement. Absolute value of R is equal to absolute value of e squared, and e squared is greater than 1. Therefore, for this case, the partial sum does not exist because it diverges, right? It grows bigger and bigger and bigger. So it diverges, so the partial sum does not exist. So those of you who will be taking calculus 1, 2, and 3, you'll delve deeper into the quantities that diverge and quantities that converge and their properties. So all this is alluding to that, which is coming up for those of you who will be taking those courses. Okay. Let's do another example. So here they want us to determine the common ratio, the fifth term, and the nth term of the geometric sequence. Okay, so determine there are several things they want us to do. Determine the common ratio, the fifth term, find that, and the nth term, which is the formula, right? So this is the formula that they want us to find for the nth term of the geometric sequence. Okay, so let's find the common ratio first. The common ratio, they already tell us that this is a geometric sequence. So all we have to do is just find one ratio, and we know it's going to be the same the rest of the way. Okay, so I'm just going to take the easiest numbers here. R would be square root of 2 over 1, or square root of 2. So this is the common ratio. R is square root of 2. Okay, so that is that. Then the fifth term. Okay, so this we have 1, 2, 3, 4 terms here. So the fifth term is, well, let me remind here that we know that any geometric sequence has this form, an times a times r to n minus 1, right? This is for all geometric sequences. This is their nth term. But now we have to adjust it for this example. So we know that the first term is 1. We just calculated the common ratio. And we know we're looking for the fifth term. So n would be 5, right? So let's calculate that. A to the fifth is equal to 1. And that's the first term, right? That's the first term we have here. 1 times square root of 2, which is the common ratio, and then 5 minus 1. All right? So 1 is just 1. Multiplying by anything is itself. So here we have square root of 2 to 4th power. And what is that? That is basically 2 or 4, right? If you raise square root of 2 to 4th power, you get 4. Okay, so let me make sure. Yes, so you can rewrite this, or you can use your calculator. You can use your calculator here. Square root of 2, square root of 2, and raise that to 4th power, and we get 4, right? But you can also, you don't need the calculator. What you can do is use the properties of radical expressions, and which we learned in Math 124 and Math 126. So rewrite the inside as 2 to 1/2 power with the 4 on the outside. Then apply the properties of exponents. So this gets multiplied, the outside power gets multiplied by the inside power. So you end up with 2 to 4 over 2 power. And that is 2, right? 4 over 2 is 2, and then you get 4. So I just thought I mentioned this in case you are asked to, or the coordinators ask you to take an exam that doesn't allow you to use the calculator, in class at least. For homework, you can use your calculator, but for in-class exams, it's their call, it's the coordinator's call what you can or cannot use. So manually, we could easily calculate that. Okay, so the other thing they ask us is find the nth term of the geometric sequence, right? That's just easy. So we're just leaving so the nth term of the sequence term we can find by simply plug in what we know, which is the first number, first digit in the sequence and the common ratio, and leave it like that. Don't touch the n. We'd like to keep that. So this will be an equals 1. I'm not going to write, but this will be r is square root of 2 to n minus 1 power. Okay, so that is our nth term of this geometric sequence. Okay. Let's do another one of these, and once again, this is the same thing, but a different example. So to serve space and time, let me call this part A then. If you don't mind, I'm going to call this part A, once again, this one that we just did. And this next one, I'll call that part B. B. And here's the sequence that we are given here. 5 to C plus 1, 5 to 2C plus 1, 5 to 3C plus 1, and then, of course, the 3 dots that indicate this is an infinite geometric sequence. So once again, we're looking for the same things. We're looking for the common ratio. So common ratio is a question. The 5th term is a question, and the nth term is a question, just like the previous example. Okay, so solution here. Okay, the easiest one is to find the common ratio. Let's take the easiest ratio here. Again, this is we are told this is a geometric sequence, so we expect to have a common ratio. So we have, I'm just going to divide this by the first digit, divided by 5, right? And then using the rules or properties of exponents we learned back in Math 124, This will be, we can rewrite this as 5 to c plus 1 times 5 to negative 1 power, right? Just bringing this up. This 5, when you bring it up, it has, the power becomes minus whatever it is. If it was 3, if this was 5 cubed, this would be 5 to minus 3 power. If this had a power of 4 in the denominator, when you bring it up, it becomes 5 to minus 4 power. So I'm just applying these properties of exponents that were discussed way before in Math 124. And I think we reviewed it in Math 126 in Chapter 1. Okay? So when the bases are the same, and you're multiplying two numbers that have exponents, and the bases are the same, you can simply add the powers. So you say 5 to c plus 1 minus 1, right? We're just adding all the powers for these two because the bases are identical. If one of these bases was different, then we could not add the powers. We can only do this because the bases are identical. So 1 and minus 1 add up to 0, so we have 5 to c power. 5 to c power is the common ratio, like that. Okay. Like that. Okay. So the next thing we have to do, we did that, is find the fifth term. Just like previously, we know that any geometric sequence has this form, right? We know that. So let's start with that. So knowing that a sub n, or the nth term, is equal to a times r to minus 1 power, then let's plug in. We have a, that's the fifth term, so a5. A is the first digit, which is 5. R is the common ratio, which is 5 to the c power, right? And n minus 1, that would be 5 minus 1, right? Because this is the fifth term. So 5 minus 1. Okay. So we have, what do we have? We have 5. That's that. And then this is 5 to the c power to fourth power. And then this is an outside power, so we're going to distribute it to the inside power, which is c. Right? So we will get 5 times 5, 4c, right? I distributed that to that power. Now the bases are the same, and being multiplied, these two numbers being multiplied, the bases are the same, so the powers get added. So 4c plus 1. We can write it like that, or we can leave it like this. It's better to combine it. So like that. So we have the fifth term is equal to 5 to 4c plus 1. Okay, that plus 1 comes from the power of this 5. The bases are identical. Using the properties of exponents, we can add the powers. 4c plus 1. There. Okay, so and then they also want us to find the nth term formula for this. So the nth term of the sequence is, so a sub n, the first term, 5, times the common ratio, which is 5 to c power. As a matter of fact, I had it here. So we can just, and then, I mean almost, so right there. That's, well, not quite, so let me write it down. So n minus 1, okay? And we'll leave it like that. That's the nth term of the sequence. Okay. Let's do another example. And the fifth term is 1. Okay. And we want to find, given this information, we want to find the first 3 terms. Okay. So basically we are told that R is equal to 3/2. I'm just repeating what this information is. And A5 is equal to 1. All right? So first of all, for any geometric sequence, the screen looks a little bit fuzzy. Let me try to focus this. Okay, that's better. So we know that for any geometric sequence, we have this formula. AN is equal to A times R to n minus 1 power, right? So to find the first 3 terms, we need to know the first term, right? We have the common ratio, and for the first term, n would be 1, second term, n would be 2, and 3 for the third term, so that's not an issue. But what about the first term? We don't have the first term yet. So first thing we need to do before finding the first 3 terms is find this first term. Then we can talk about the A1, A2, and 3. So let's find this A. Okay, so we'll use the fact that A5 is 1, right? So we know that A5, or the 5th digit, is 1 in this geometric sequence. Therefore, or thus, we can write this. We can substitute for A5. I'll just put 1 for A5 equals A, which we don't know. We don't know that. We're looking for it. R is 3/2. And N should be what number for the 5th term? N is 5, right? So 5 minus 1. Okay, so let's simplify. And this is an equation with only one missing variable, right? So we can easily solve for it. So 1 equals A and times 3/2 to 4th power. Let's distribute that power into this because these are easy numbers. So we have 1 equals a times 3 to the 4th power is 81. 2 to the 4th power is 16. All right? And then what do we have? We have 1 equals 81 times a over 16, right? That's what we have. So this is the denominator of 1 on this side is 1. We have 1 whole fraction on the other side. Let's cross multiply. Or the way you like to think of it is multiply both sides by 16. It's no different. It's just two different ways of thinking about it. But cross multiplying or multiplying both sides by 16 gives us this. Gives us a 16 equals 81 times a, and therefore a is equal to 16 over 81. We would simplify this if we could, but 16 and 81 do not have any common factors. So we'll leave it like that. So that's the first term in this sequence. Now we can find, so this is the first term in this sequence. Or you can call it A1 if you like. But they're asking us for the first 3 terms. So we have 2 more terms to calculate. Let's do that. So A2 is that first term, right? A2 would be 16 over 81 times the common ratio, which we were given is 3/2. N minus 1, this is the second number we're looking for, so 2 minus 1, right? Okay, so let's simplify this. We have 16 over 81 times 3/2. 2 minus 1 is 1. And then simplifying this, 3 and 81 do have, so we have this 16 times 3 divided by 81 times 2, right? So we can simplify this. 2 is a common factor of 8, 8 times 3, and so simplifying all of this, we should end up with, and 3 is a common factor of 81, so that's 27 actually. So we get 8 divided by 27. So that's the second term, or A2. Second term. And then we have one more term to calculate, right? So that would be A3 equals 16 over 81 times 3/2 to, this is the third term, so 3 minus 1. Okay, so we have 16 over 81 times 3/2 squared. So we have 16 over 81 times, distribute this power, we get 9 over 4. Certainly we can simplify that, right? After simplifying, we get 4 over 9. And that is the third term in the sequence. Okay. Let's do another example. I hope, I keep forgetting to remind you, please pause the video. Whenever I write a problem statement down, pause the video, finish it on your own, and then look back at my solutions. I know I've been forgetting to remind you of that, but I hope you've been doing that all along. Okay, so we have here we want to find the partial sum, right? We introduced some formulas for this, the three cases we have, right? Remember that? The partial sum Sn or S sub n of the geometric sequence that satisfies the given conditions. And here are the conditions we have. The first term is 2/3, we are told. The common ratio is 1/3, and n is equal to 4. So this means we're adding 4 numbers. Let me just say that, well, I'll state that as part of the solution. So solution is here. So n equals 4. That means we are adding 4 terms, this time starting with the first number. Starting with the first number in the sequence. Okay, so this is a finite sum. It's not an infinite sum, so for sure we have an answer. So we know that for the partial sum formula is S sub n is equal to a times 1 minus r to n power divided by 1 minus r, right? And a gets multiplied by the numerator. So let's plug in with the information we have. So S4, that's the fourth, we're adding 4 terms. A is 2/3. And then 1 minus r, which is 1/3, to n power. 4 divided by 1 minus 1/3. Okay? Okay, so we're going to need to simplify this, right? Distributing this power, we're going to have 1 minus 1 over 81. 3 to the 4th is 81. So we have 1 minus 1 over 81 divided by 1 minus 1/3. Take the common denominator, 3. 3 minus 1 is 2/3. So 2/3. Okay. So we need to simplify the numerator there a little bit. So take the common denominator, 81. 81 minus 1 is 80 over 81. So S4 is 2/3 times 80 over 81. 2 over 3. If some of you might have questions, how did we get the 80 over 81 and 2/3? Here is, let me just show you that here. It's just a basic common denominator. So I'll do that for that one. So common denominator, or take the common denominator. So that would be 1. The denominator here is 1. We don't write it, right? Minus 1 over 3. Now the common denominator is 3. So this one is okay. We don't have to do anything to this fraction. This one is not. We need to get it to that point. So we'll multiply this fraction by 3 over 3. Our objective is to obtain the common denominator 3. But we can't multiply just the denominator. We need to multiply the numerator by the same number. Okay? So now we have 3 and we have 3 in the denominator. That means we can add or subtract the numerators. So 3 times 1 is 3 minus 1. And we end up with 2/3, which you see here. Okay, that 2/3 you see here is coming from that. Now, this one, for this one, once again, take the, well, I should have done that here. So it's actually that way. From here, take the common denominator. So what do we have? We have 1 over 1, all right? 1 over 1 minus 1 over 81. We know the common denominator is 81. So this one is okay. We don't have to do anything to this fraction. This one is not. To get it to the common denominator, we have to multiply this 1 by 81. But we can't do that just to the denominator. We have to do that also in the numerator. So we end up with 81 times 1, which is 81, minus 1, which gives us the 80 over 81 that you see here. Okay? So that one and that one we had to do to obtain these numbers. Okay, and I will clean this up before I post it on Canvas for all of you. Okay, now this complex fraction we've already talked about in previous videos about the easiest way to simplify them, right? So take the farthest numbers from each other, or the numbers that are farthest away from each other, multiply them and put them in the numerator. Then multiply the numbers that are closest to each other and put that product in the denominator. So I'm going to do that next. So S4 is equal to 2 over 3 times 80 times 3. Right? Those are the numbers farthest away from each other. Multiply them, put them in the numerator. The numbers closest to each other, multiply them, and put them in the denominator, like that. Okay? Now we can simplify. 2 and 80 have common factors, and so on. So after simplifying and multiplying by this 2/3, so this 2 and this 2 cancel out. This 3 and this 3 cancel out because everything is being multiplied, right? So we end up with the 80 over 81 ratio. Okay? So that's the sum of the first 4 terms in this geometric sequence. Okay, let's do another example. So we want to find the sum of the following geometric sequence, which is 1, I actually should say geometric series, because this is no longer, I mean, these terms are coming from a geometric sequence, but the way they're written, this is a series. So geometric series. So that way I fixed that. Geometric series. This is an interesting example, so I picked it for that reason. And plus 1 over 4 minus 1 over 8. And then we have a gap here. And then we have minus 1 over 512. Okay. Find the sum of the following geometric series. Okay, so one way of solving this is, first of all, so basically they want us to add all these numbers, but this gap doesn't show us what numbers were in between. So we need to know what those numbers are. Okay. So the common ratio, so we have the first number here is 1, right? The common ratio, let's find that. Common ratio would be minus 1/2 over 1 divided by 1, which means R is equal to minus 1/2, right? So if we look back at or let me write it down here, at the partial sum formula for the geometric sequence, we know that the partial sum is equal to A times 1 minus R to n power over 1 minus R, right? So here we know the A, the first digit, we know the common ratio, but we don't know how many numbers we're adding. We need to know n, right? So there's a gap here, and presumably this is the last term, right? So that's the last term. So we still need to know how many numbers in this finite geometric series we're adding, okay? And we don't know that. So because there's a relationship here, you can quickly see that the denominators are 2 to some power, right? So this one would have 2 to 0 power 1, which is not there. 2 to power 1 or 1 is 2. 2 to second power is 4. 2 to third power 8. So clearly there is a pattern here, and we need to use that pattern to complete this series. In other words, use that pattern to find the missing terms. We should be at the last term in no time, right? Because these are power terms. So we quickly get to that. So let's do that, because that'll help us figure out how many terms we have. So listing, and let me write that down. Because we don't know how many terms we are adding, list all numbers, including the missing ones. We can do this because this is a short list. If this was a very large list, then we wouldn't do this. And we would have more information to answer the question. But here, the idea here is that, okay, it is a very, very easy pattern
that we can easily find. And noticing also that we have alternating algebraic sign. Keep that in mind. So the next one would be positive 1 over 2 to the 4th power, or 1 over 16. And the next one after that would be negative 1 over 2 to the 5th power, which is negative 1 over 32, and so on and so forth. Okay? So the pattern is very easy. We can easily complete this list, including the missing numbers. And when we do that, we have this list. I'll try to fit it across the page. We have 1 minus 1/2 plus 1/4 minus 1 over 8. So far, we were given all this. Now, these are the missing terms, right? I'm going to write them in red. Plus 1 over 16 minus 1 over 32 plus 1 over 64 minus 1 over 128 plus 1 over 256, and then minus 1 over 512, which we were given, right? So let me see if I can put all this on the screen. So now, where you see the dot dot, it was just these 5 terms. And we figured it out because we knew the pattern in here, including the alternating algebraic sign. It was just 2 to some power. And 2 to 0 power would be 1, the denominator of the first one. Then 2 to first power would be 2, 2 to second power would be 4, 2 cubed would be 8, and so on and so forth. And 2 to some power would give us the 512. Okay, so now we know that. How many numbers are we adding? Let's count, right? Let's count. It should be 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n, thus, n is equal to 10. All right? So now we can use this formula with everything known. The first term, the n, the common ratio, and everything, right? So let's do that. And therefore, the sum, or S, is, because A is 1, I'm not going to write it. Okay? We no need to write that. 1 times anything is itself. So I'm not going to write 1 for A. I'm going to just write this, the rest of this. So we have 1 minus the common ratio was negative 1/2. The power here would be 10 for all of that, divided by 1 minus 1/2, which is the common ratio, right? So I plugged in into this formula with the information we have, and I left that part out because A is equal to 1, which is the first digit in the sequence. Okay, so the rest is just a matter of doing the algebra and simplifying. So minus 1/2 to 10th power. 10th power, because it's an even power, cancels out this negative, so it becomes positive. So we have 1 minus 1 over 1024, right? 2 to the 10th power is 1024. Let's make sure of that. So 2 to 10th power, 1024. Okay, and that's what you see here. And this minus is gone. The minus you see here is this one, not that one. That one is gone because of this even power which cancels that. If that was 9, we would preserve that negative, multiply it by this, and we would have a positive here. But it's an even power, so it cancels that. We only have this minus left. Okay? And then this minus times that minus makes it positive. This times that. So 1 plus 1/2. Okay, so let's take the common denominator. I hope you're comfortable. If you were not comfortable with taking the common denominator, I hope now you are. So taking the common denominator here, we have 1024 minus 1. That's for the numerator here. And the denominator is just easy. 1 plus 1/2 is 1.5 or 3/2. Okay, so this is another complex fraction that we need to simplify. I think on the previous page I said complex number, not complex number, complex fraction. I apologize for that. But this complex fraction we can easily simplify. So that's 1023, right? So we have 1023 over 1024 divided by 3/2. So we know how to simplify complex fractions, right? Take the product of the farthest terms, put them in the numerator, like that. Take the product of the nearest terms and put them in the denominator. Okay, so now after simplifying, we get 341 over 512 after simplification. Okay, we have that. All right, let's do another example. Determine if whether the infinite geometric series is convergent or divergent. Again, these are the things you'll see more in calculus classes. Divergent. If it is convergent, find its sum. Of course, please remember that if the infinite series diverges, then it does not have a sum. Okay, remember that slide? Or let me find that out from here. If I can do that very quickly. Right there. So remember this one? When we were talking about cases, case 1, case 2, case 3, we have, in this case, they're asking us to look at these infinite series, geometric series, and see if they converge. Let me box that, converges, and that one diverges. So if it converges, we can find the sum using this formula, a over 1 minus r. For an infinite geometric sequence. If it diverges, then we don't have to bother using any formula. It just does not, the sum does not exist. Okay, this was on page 2 of the lecture notes. Okay, so, and this has part A and B. So here's part A. This is the series, geometric series, 2/5 plus 4 over 25. Notice when we have series, we have plus or minuses, right? No commas. The commas are for the sequences. For series, it's the plus or minus because we're adding. A series is a sum. 8 over 125 plus ... Okay, so the first thing for us to determine is whether this infinite geometric series is convergent or divergent. And the way to do that is we find the common ratio. So, solution here. So we know that if absolute value of r is less than 1, then the series converges. I'm just reminding us of what we had on the second page of this lecture series for this video. If absolute value of r is greater than 1, then the series diverges and the sum does not exist. Okay? All right, so let's do that. Let's find the common ratio for this one then. R is equal to 4 over 25 divided by 2 over 5. So this being a complex fraction, we have 4 times 5 divided by 25 times 2, right? After simplifying, we get 2 over 5. So let me write it here. Absolute value of 2 over 5 is less than 1. So the series converges. Okay? So we determined that. And they say if it is convergent, find its sum, the sum of this series. So let's do that. So we're going to use that formula, this one. For an infinite geometric sequence or series, in this case series because we're adding, the way it's presented to us, it's in series form, not in sequence form. Otherwise, it would be in commas. So if we have an infinite geometric series, if the absolute value of the common ratio is less than 1, which it is in this case, the sum converges, and we find the sum using this formula. Okay, so let's apply that. We know that for this case, S is equal to A over 1 minus R. Okay, so we're going to apply that. So S is equal to A is 2/5. So 2/5 divided by 1 minus R, which is again 2/5. Okay. Okay, so take the common denominator here. We have 5 minus 2, so that would be 3 over 5. And simplifying this, we get, so 2 times 5 divided by 5 times 3. The 5 and the 5 cancel out. We get 2/3, right? That's the sum of this infinite geometric sequence, or series. So if you add, what does this mean? That means this series, geometric series, has infinitely many terms. If you add all those infinitely many terms to each other, if you add them all up, you get 2/3. Okay? We found that out here. So for part B, the infinite geometric series that we are being given is as follows: 1 minus square root of 2 plus 2 minus 2 square root of 2 plus 4 minus dot dot dot. So notice the alternating algebraic sign there. Okay, so we have to, first thing we have to establish whether this is convergent or divergent, right? So let's establish that. So R would be any of these numbers divided by the number previous to it, right? Minus square root of 2 over 1. So that is minus square root of 2. Okay, so absolute value of minus square root of 2 is equal to absolute, it's equal to square root of 2, and that is greater than 1. That is greater than 1, so the series diverges. That's the first thing they asked us to establish. That the series diverges, therefore the sum does not exist. Thus, the sum does not exist. Okay. So we have come to the end of another video here. But when I was looking through your book, I mean, the book that based upon which I'm preparing these videos, in this edition of the book, on page 801, example 3 was a really good example. I thought it was an interesting example. So one thing I want to mention at the end of this video is please read and understand the example number 3 of page 801. Okay, so I thought that's a good example to have a look at. That is in case if you haven't already gone through the book, so that would be a good example to make sure that you pause and understand as much of it as you possibly can. And of course, this is at the time I'm recording this video, and by the time you see this video, the book edition may have been changed. So the topic hasn't changed, so the videos are still good, but the edition may have been changed, which means you may not be able to find that example. That's the only thing. And so if that's the case, then no, don't worry about it. Okay, so I'm glad that you persisted through this again, and thank you for that. And for now, have a nice day, and I'll see you next time.